Welcome back to Depth Talks Education. We are continuing with our calculations in the mole concept and the volumetric analysis. So let us look at how to calculate the number of moles of water crystallization and its percentage. That's the percentage of water crystallization in hydrated compounds. So let us look at this number here and we see how to go about with that. So we have been given that 20 cubic centimeters of a solution containing 14.3 grams of hydrated sodium carbonate, it's here, with X moles of water crystallization, as you can see, in 250 cubic centimeters, required 20 cubic centimeters of 0.4 capital M hydrochloric acid for complete reaction. So the questions are here. We get the number of moles of water the number of moles of hydrochloric acid that reacted. Then we get the number of moles of sodium carbonate that reacted and determine the molarity of the sodium carbonate solution. Then we calculate the molar mass of sodium carbonate, hydrated sodium carbonate. That's the mass of 1 mole, molar mass. Then after that we determine the number of moles of water crystallization, X, in this compound, that's in the hydrated sodium carbonate. And then we calculate the percentage of water crystallization in the hydrated sodium carbonate. So what do we do first? We first collect the data. In our data here, we have been given the hydrated sodium carbonate, that's sodium carbonate dot X water. We have been given the volume is 20 cubic centimeters. And then the concentration is here, it is 14.3 grams per, or in 250 cubic centimeters, that is per 250 cubic centimeters. So the 14.3 grams of the hydrated sodium carbonate was dissolved in water to make 250 cubic centimeters of the solution. Then we also have hydrochloric acid. So for the hydrochloric acid, we have it here, that 20 cubic centimeters of hydrochloric acid was required for the complete reaction. In this case, the molarity of the hydrochloric acid is 0.4 capital N. We have everything that we need. So let us go straight to the calculation, starting with A Roman 1. In A Roman 1, they want us to get the number of moles of hydrochloric acid that reacted. So we come to hydrochloric acid, the molarity is here, it means 1,000 cubic centimeters of hydrochloric acid contains 0.4 mole. And then what of the volume that reacted, the 20 cubic centimeters of hydrochloric acid. So it contains, we cross multiply, 0.4 times 20 over 1,000 mole. And let us get, in this case, our number of moles of hydrochloric acid that reacted. So it is 0.4 times 20, and we divide by 1,000. Our answer is 0.008 mole. Let's go to Roman 2. In Roman 2, they want us to calculate the number of moles of sodium carbonate that reacted. In this case, we don't see the molarity of the sodium carbonate in this case. So what shall we do? We shall write the equation for the reaction between hydrochloric acid and then the sodium carbonate. And then we use the mole ratio. So let's write the equation. So we are having hydrated sodium carbonate. Now, in the reaction, we shall not include the water of crystallization because it will not take part in the reaction since it is already a solution. It will be the sodium carbonate that will take part in the reaction with the hydrochloric acid. So we shall have sodium carbonate solution. Don't again write water crystallization there. It is reacting with hydrochloric acid. And our expected products here are sodium chloride. We shall also get water, and we shall get carbon dioxide gas. So let's balance the equation first. 2 sodium atoms here we have. 1 we multiply sodium chloride by 2. 2 chlorine atoms on the reactant side, only 1 multiply hydrochloric acid by 2. 2 hydrogen atoms they are here. 1 carbon atom it is there. And 3 oxygen atoms here they are. So our equation is now balanced. We shall use the mole ratio here or the stoichiometry of the reaction on the side of the reactants to get the number of moles of sodium carbonate that reacted. So we are looking for the number of moles of sodium carbonate. It goes on that side. We start with hydrochloric acid and we start with what we are seeing from the equation. We say 2 moles of hydrochloric acid reacts with 1 mole of sodium carbonate. Then what of this number of moles here? The 0.008 mole of hydrochloric acid, it reacts with, we cross multiply 1 times 0.008 and we divide by 2 mole of sodium carbonate and we get 0.004 mole. And that's the number of moles of sodium carbonate that reacted. Now let us proceed and we look at the other parts of the question. Allow me to remove the upper part as this part is just as you can see. We are good to go because we have already the data collected as we can see in red. So let us go to part B, which says we get the molarity of the sodium carbonate solution. So molarity is the number of moles of a substance in 1,000 cubic centimeters. Now this is the number of moles of sodium carbonate that reacted and the volume that reacted is 20. It means that, that's now part C. It means that 20, this is part B. It means that 20 cubic centimeters of the sodium carbonate solution contains 0.04 mole. And then what of 1,000 cubic centimeters of the sodium carbonate solution? It contains, and we cross multiply 0.04 times 1,000 over 20 mole. Let's see what we get from here using our calculator. So it is 0.04 times 1,000 and we divide by 20. So this one has given us, it is 0.004. So it has given us 0.2 capital M, and that's the molarity of the solution. Let us try to prove 0.004 times 1,000 out of 20. So we have 0.2 capital M, that is the molarity of the sodium carbonate solution. Let's go to the next part in this case. In the next part, it says that we have to calculate the molar mass of sodium carbonate x water. The molar mass is the mass of 1 mole. And what shall we do in this case? We have to compare the molarity here, which is in moles per liter. We relate it with the concentration in grams per liter, which we don't have here. This is the mass in 250 cubic centimeters, not in 1,000 cubic centimeters. And then we have to convert this mass here in 250 cubic centimeters to the mass in 1,000 cubic centimeters. And that is in our part, it is in part C. Calculate the molar mass of sodium carbonate x water. So in part C, let us change that mass in 250 cubic centimeters to the mass in 1,000 cubic centimeters by saying 250 cubic centimeters of this solution of sodium carbonate contains a mass of 14.3 grams. And then what of 1,000 cubic centimeters of the solution? It contains, we cross multiply 14.3 times 1,000 over 250 grams. And what do we get in this case? We have to look for the concentration now in grams per liter first, and then we relate it to the molarity, which is the concentration in moles per liter. So it is 14.3 times 1,000, and then we divide by 250. So we have 57.2 grams per liter, S being our concentration in grams per liter. And then this one here, we relate it to the molarity. This is grams per liter, this is moles per liter. It means this number of moles weighs 57.2 grams. And then what of 1 mole? The mass of 1 mole, or the molar mass. So we shall finally say that 0.2 mole of the sodium carbonate, hydrated sodium carbonate, weighs 57.2 grams. And then what of 1 mole of the hydrated sodium carbonate? So it weighs, we cross multiply 57.2 times 1 over 0.2 grams. So we are getting the mass of 1 mole of the hydrated sodium carbonate. And this one has given us 286. This is the mass of 1 mole of the hydrated sodium carbonate. Now, let's go to this part here that we determine, or we calculate therefore the percentage. We first get the number of moles of water crystallization X in the hydrated compound. The number of moles of water crystallization in the hydrated compound, that's now D1. So if we are to get the number of moles of water crystallization, we are going to say the whole of the sodium carbonate hydrated, that's sodium carbonate X water. The total mass is 286. That's the relative formula mass. So let's get the value of X in this case. Sodium, we have 2 atoms, that is 23 times 2 plus 12 plus 16 times 3 plus X times the whole of water, 1 times 2 plus 16, and we close the bracket and we equate this one to 286. So this one here is 46. 46 plus 12 is 58 plus 48 is 106. So 106 plus 16 times 2 is 18. So we have 18x should give us a total of 286. Then let us work, or we look for the value of x in this case. Allow me to remove this one here as we move slowly. So in this case, our 18x, we are subtracting 106 from both sides, is equal to 286 minus 106. So 18x is equal to 286 minus 106 is 180. So what is our x? X is equal to 180 over 18, which is very important, and x therefore is equal to 10. So the number of moles of water crystallization here is 10. That's the value of x. And then let us get the percentage. I can now do away with this part here. The percentage of water crystallization. So the percentage of water crystallization will be equal to the mass of water crystallization. So let us say the percentage of water of crystallization will be equal to the mass of water. Since the value of x is already 10, we shall say 10 times the mass of water, x is 10, out of the total mass, which is 286, and we multiply by 100. So what do we get in this case? This one we got it to be 100, and in fact it is equal to 18. That is 16 times 2. So it will be 10 times 1 times 2 plus 16 out of 286 times 100. So this one is 180 over 286 times 100. And let's see what we get from here. It is 180 over 286 times 100. And it is 62.93706,294%, which can be approximately 62.94% if we have decided to round off to 2 decimal places. So we have got, in this case, the percentage of water of crystallization over there. So thank you so much. This is Step Talks Education. Thanks for watching.